What is up, most distinguished patrons of this channel? So for today, we are going to be diving into the world of how to TIG weld stainless steel. I have not done a video directly on this yet, and I think it's time to do that. Stainless steel really isn't that hard to TIG weld, but there's a lot of things you need to know to do it right. So with that said, let's get into it. Now, stainless steel is not technically that hard to weld. It really welds like steel, and that's why I tell anyone who's wanting to learn to TIG weld stainless, then get good at steel first because it's a cheaper material. Then once you're really good at steel, go over and do some stainless steel welding because it's honestly not that much harder than that. The thing is that you got to understand about stainless is it requires what I call attention to details. With steel, you can get away with a lot of things that simply don't work for stainless. So like your heat input on normal steel is not really a big issue. Stainless steel it is because it will oxidize on you. Gas coverage is generally not really a big issue with TIG on steel. With stainless steel, it tends to be. And there's also significant health issues regarding welding and working with this stuff that I have to cover as well. And that's the first thing we're going to talk about. So I'm not going to sugarcoat this, guys. Stainless steel and chromium-based alloys are not good to work with for your health. That includes welding them, grinding them, and doing anything that can turn this into fume or dust is absolutely terrible for your health. What's known as hexavalent chromium exposure from working with this stuff is almost guaranteed lung cancer. So in my opinion, if you want to do work with stainless steel, you should be wearing a filter mask of some sort or a powered air purifying respirator anytime you're working around with this stuff. Now, I'll be honest, the TIG process does not produce much fume with this stuff. So from a weldability standpoint, your exposure to hazardous carcinogens working with this stuff with TIG is limited. However, you still have to grind this stuff. You still have to cut this stuff. And if you're plasma cutting, which is about the worst with this stuff, all of those things will put hexavalent chromium into the air, and it will cause the potential for lung cancer. And I'm not saying this lightly, guys. This stuff is absolutely terrible for your lungs. And I'm going to repeat that many times probably in this video. Get used to it. You need to have the mindset that this is nothing to screw around with. So with that safety disclaimer put away, let's talk a little bit about the material itself. So stainless steel comes in a number of what we'll call grades. The most common grades you might run into would be something like 304, 316, 409. Those are probably the most common. When you're dealing in tool steels or basically tooling, you're going to find a whole bunch of stainlesses that are less common. I mean, they are common, just not to build stuff out of. And those typically are heat treated or have different processes that are involved in the weldability of them. So for the sake of what we're dealing with today, we're just going to be talking about 316, 304, and 409. Now, a majority of what you would find in industry or for repair work or whatever typically would be 304 stainless. That's what likely this is, that's what this is, that's what this pipe is, this probably is, this over here, this piece of exhaust is not. So we'll start off with the 304. 304 stainless has really good corrosion resistance. It has pretty high nickel and chromium contents. And for the most part, it's reasonably affordable. I mean, this stuff is expensive no matter what, but it's reasonably affordable and it meets the needs of most things. Very commonly used, say, in a dump box for a plow truck that's ordered with stainless, they use 304. 304 is non-magnetic, and I got a magnet here, and you can see how strong that is. It's known as non-magnetic. However, when I bring this magnet close to it, I can feel it. You can see it kind of moves. But for all practical purposes, this will not stick to it. So a good test that you can do to identify what form of stainless you have is if a magnet sticks to it very strong, either it's a carbon steel that looks like stainless or it's probably 409. This 304 stainless non-magnetic. 316 stainless is generally even less magnetic than this, but for all practical purposes, you're going to have a very hard time determining if it's 304 or 316. With 316 stainless, which again looks just like this, that stuff is typically used in food plants, in piping, or in things that need chemical or high corrosion resistance. So that would be a much more expensive product, far less common. And a lot of things simply aren't built out of 316 because the added costs for the extra chromium and the extra nickel just aren't worth it. So if you need to do a repair, it may be in your best interest to figure out what it's made out of. But if you can't figure that out, we'll talk a little bit about the filler rod selections, because it does matter what grade or what type it is to determine what filler rod to use. Now, I'll quickly talk about 409 stainless. This stuff kind of has always bothered me. This is a piece of exhaust. They market it as stainless, and it technically does have chromium and nickel in it. The problem is that it's not nearly as corrosion resistant as 304. In my experience, 409, when it gets hot, loses all of its corrosion resistance, and this stuff will rust just as fast as mild steel, especially if you get like a off-spec, I guess, Chinese-made exhaust system that claims to be 409. Yeah, it might be, but man, they rust just as fast as bare steel. The easiest way to determine this being 409 is you take your magnet, and if it sticks to it like that, yet it's very shiny and doesn't appear to have too much rust, that would be 409. And you can even see on this, in the area of the heat affected zone, hopefully you can see that, it's starting to turn red with rust. This is 409. My recommendation is do not use this stuff for anything other than exhaust. It simply isn't worth the additional cost because it offers very minimal corrosion resistance. But 409 typically is magnetic. Also, if you have a part that you're doing a repair on, don't be surprised if it's 304 and a magnet sticks to it. As stainless steel gets worked and formed, it can become magnetic depending on the alloy. So again, the magnet test is really only good for bare base material like these. Okay, less so for actual machine parts or anything that was formed or hammered or forged or whatever. So keep that in mind. So let's talk a little bit about filler materials here so you understand what we're dealing with. You have your common 304 and your 316, two very common stainless steels. And then these are all filler rods that can be used for them. Let's start out with the 304. Technically, you can weld 304 stainless with 304 filler. It's not very common. You can weld it with 308. That's probably the most common filler that you would use, and it would work. You can technically weld 304 with these other ones. However, they have a different mix of chromium and nickel and overall performance. And honestly, you're always best welding it a particular alloy with what it was really designed to be welded with. So you can generally go up in grade. So like you could weld 304 with all of these. You would not really want to weld 316 with 308. And the reason's simple. This has higher corrosion resistance, and welding it with a undergrade, we'll call it, a lower grade of stainless, you're not going to get the performance of the base material. So the goal is always to meet the performance of the base material or above that, not to go below it. So 304, again, you can use 304, 308 would be the most common. 308 is not typically sold in sheets or material. That's generally specified for filler material. 312 is, again, a filler material, although it does exist as a base alloy that you could buy. Very uncommon. Most of what you're going to be dealing with are these two. 316, like I said, that's a very common alloy in piping and high corrosion resistant environments. And generally, you just weld 316 with 316. Now, the L here stands for low carbon. Some projects, aka if you work for a company and you were working with some specific alloy that they wanted to specify non-low carbon, so it would just be known as 308 filler, that may exist. But for all practical purposes, you should be buying the L version of this, and that will take care of what you need to do. Only should you change that if a job requires that. And again, that will generally be specified. Now, the outlier of this group is what's known as 309L. 309L is used to weld typically 304 to mild steel. The alloy is basically designed to do dissimilar metals. Can you use 309 to weld any of these? Yes. Will you get the same performance compared to these alloys with that? Probably not. So only typically use 309 to weld stainless to steel. You probably shouldn't be using it for any other purpose. It does work for that, but again, you probably shouldn't. Now, there is a 409 wire that is available. Nobody uses it, and technically 409 stainless should be welded with itself generally, but pretty much everybody out there either welds it with 309, which would be very acceptable, or 308, just so you know. It's very common with exhaust systems that guys will just MIG weld or even flux core weld stainless 409, and the welds are just going to rust out of that almost immediately. So I would recommend, if you're working with 409, stick with 308, or probably even better is 309. Now, the last thing I'm going to mention on these fillers, 312 is a very useful filler for welding unknown steel. It's very common in stick welding to buy what's called problem solver rods. They're all 312 stainless. This alloy has a really good ability to weld certain cast irons, and if you don't know the grade of material you're dealing with, like for stainless, this typically will cover it. And this also has the ability to weld certain tool steels as well as spring steels better than maybe 308 and 316 and even 309. So look at 312 more as a problem solver. It pays to have some on hand for some kind of casting, that and just pure nickel rods, but it's something that can get you out of a bind if you ever need to repair something. So you understand a little bit more about the base material, a little bit more about the filler rods. Let's talk about the reactivity of this material. When I say reactivity, I mean its sensitivity to exposure to oxygen. When you TIG weld material, you have a little gas cup that surrounds your tungsten, and you have a gas envelope that shields that molten material and that hot material from oxygen and the air you're breathing. Well, stainless steel is one of those materials that we can call it a reactive material. It doesn't like to be exposed to oxygen. What gives it its stainless or its resistance to rust is that chromium and that nickel. Well, when you weld it and you don't have adequate gas coverage, what ends up happening is that red hot metal that you just welded oxidizes in the air, and then it loses its corrosion resistance due to all that oxidization. Now, there's two distinct problems regarding that stainless steel faces. One is just straight oxidization. In this welding art piece I made, I used oxidization to create color to be able to make this art, right? So in this case, the oxidization is both desirable and it's what I'm trying to achieve. When you're actually welding things that need corrosion resistance, this oxidization is undesirable. Now, this gold stuff here is actually not stainless filler, that's silicon bronze. But when you look up here, this blue and the gold here, that's all oxidization. It's very common for people to think that any color on stainless steel means it's junk. That's simply not the case. Stainless steel is not like titanium, which is super reactive, where color on titanium means the material is compromised. Color and oxidization on stainless welds is not an indication that the weld is weak or the material is compromised. It is an indication that that metal was hot and it reacted with oxygen. Where the problem comes in with stainless is when you weld it and it turns cooked gray, and I'll show you some of that in this video later. That becomes a problem because that level of oxidization is going to be far beyond the surface. It's going to be into the base material. It's not going to be easily removed. You're going to have to grind it all out, and it will rust. The whole purpose in using stainless steel generally is to resist corrosion or to have better performance against acids, etc. So welding it and producing welds that have no corrosion resistance due to oxidization is very bad, because a finished product is going to rust on the welds and everything else might look fine, and that may be undesirable. So having adequate gas shielding is important. However, for less critical things, some color like blue or red really doesn't matter. What matters is it's not cooked in gray. Now, there's a second distinct problem that stainless steel faces, and it's called carbide precipitation. In a simple, broken down way to explain this, carbide precipitation is a change inside of the base material where it loses both its corrosion resistance and its actual performance. Carbide precipitation is what a lot of people think the oxidization is. That's simply not the case. When you weld stainless with TIG, your temperature swings, so from base material cold like this is to molten, is so fast, and then, well, of course, back to like solidified is so fast, you generally don't get poor grain structure and carbide precipitation in the material during welding. Carbide precipitation commonly happens if, well, I guess if you cook the material so bad to the point that you're going to get it internally via welding, but it's much more common in manufacturing of the stainless than you would find from welding it. Again, in a single pass TIG weld, you simply don't put enough heat in it for long enough for that to happen. But yes, if you were to completely cook out the stainless by doing, say, 7 passes on something and the whole thing is just gray, yeah, you're probably going to have some carbide precipitation. But again, the difference there is that level of the decline in the base material is going to cause both strength issues and performance issues with corrosion. It is a serious defect. Simple oxidization in color is not really a defect. And in most cases, you can simply wipe this stuff off with some cleaner and a metal brush, and it'll clean right up. It's that dark gray oxidization that a steel brush or a stainless brush and cleaner isn't going to cut. Even those electrolysis cleaners aren't going to necessarily take care of that. And again, I'll show you in a minute what I'm talking about. It's very common with steel to weld with these number 7 or number 8 cups. This happens to be a stubby lens, and this can work depending on the situation to provide adequate gas shielding. However, this is not generally recommended for stainless. Generally with stainless, you want a number 10 or number 12 cup. I have a little kit here. This, which is a number 14, you can see how much wider that area is. It requires more shielding gas, so 30 to 40 cubic feet an hour versus maybe 15. So you need more shielding gas, but it covers more of an envelope of area. And that becomes important because as you weld stainless, the trailing area, the area that you have welded that the weld is still cooling, that needs to be shielded from oxygen the best you can just so it doesn't start oxidizing. And one of the best ways, and pretty much the only way to prevent that, is to use a bigger cup with more shielding gas. Now, a lot of people think that it's an absolute requirement that you get some monstrous like number 20 cup or something to do stainless. That's simply not the case. From a recommendation standpoint, I would look for a number 10 or a number 14 cup and start with that for stainless steel welding. So yes, you're going to end up using a lot more argon than steel, but hey, you're welding stainless and you want corrosion resistance, so you really need to do it anyways. It's just the nature of the beast. It's why stainless costs so much to weld in comparison to steel. So let's do some actual welding. What I'm going to do is demonstrate how the gas shielding envelope matters when it comes to the weld. And I have the machine set for 60 amps. I'm going to run a pass with this giant number 14 cup at 40 cubic feet an hour, and using the same 60 amps, I'm going to reduce the flow to about 20 cubic feet an hour with this number 7 or 8, number 8 cup. And I'm going to run 2 welds on this, and then we're going to look at them up close to get a better idea of what's going on. So 60 amps was actually a little bit hot, so I was somewhere probably around 50 on it. This material is a little thinner than I expected. Anyways, this weld right here was done with the larger gas cup, and you can see a very consistent color. These are short welds, and I did that kind of on purpose to kind of show how much better the shielding gas is with a larger cup. More or less, as the tungsten's right here, this area is still shielded by that gas shielding envelope with the larger cup. When you get over here, which I ran at approximately the same foot pedal position, so the same amperage, just with a number 8 versus a number 14, as you're welding, more of this area becomes unshielded and reacts with oxygen simply because the area around that tungsten, the gas shielding, isn't as good. And that's why you start seeing, okay, this looks pretty good, and then over here it starts reacting right here with oxygen and it starts turning dull red. Now, none of this is really what I would consider cooked, and I'll show you in a second when I buff this all off with a brush, it's going to look pretty good. Now, you have to understand that even with a smaller cup, you can get very low oxidization, and that is where I did this. This little guy looks a lot shinier, and that's simply because I ran less amperage. And the reason I bring that up is because with stainless, a lot of people have a real bad tendency to run really low amperage to try and get the weld to be shiny silver, because that's all you really need to do is just run super low amperage. And yeah, it's going to come out silver even with a number 10 or a number 8 cup. The problem is when you run cold, you're going to have less penetration, less fusion, and higher probability of a lack of fusion. And you don't want that with stainless or for anything. So you need to use an appropriate amperage. Now, both of these are a little bit on the hot side for this material. You can tell because it's sunk in and has that line down the center like a V shape. So these are a little bit hot. This is a little bit cold. But with an appropriate gas lens, that's a number 12 or number 14 and an appropriate amperage, you can get very acceptable welds. So let me go get a stainless brush and I'm going to brush these and let's look at them. So you can tell looking at this, basically all of that color just comes right off. You don't really see any dull grays in here. This, due to how much it's sunk in, looks a little bit darker, but it's basically, from my view, as shiny as these. This is the most shiny out of them. But that has a lot to do with the fact that it's sitting above the plate and it's reflecting light differently. These two are both sunk in. But anyways, nothing here with the color is defective. The weld is not weaker because of it. This is not titanium. With titanium, all that color you saw in this one and this one would mean the base material is junk. But we are all acceptable on this side with this. Now let's take a look at the back side at what we have. So here on the back side, I took the liberty of brushing these welds a little bit, and you can see what we have here. Basically, all the oxidization colors are gone. However, there's this gray area that you can see around the weld, here and here, even internally on the bead there. All of that is oxidization of the stainless that will rust. This is why with stainless steel, to get an absolute clean backside of a weld, you must purge it with argon so that it cannot react with oxygen in the air and have this happen. Now, it's very common with ornamental stainless work like hand railings and such that I've seen, where because they're not purging the area good enough around where they're welding on the surface, if you get any of this on the surface and it doesn't clean off with a brush, it will rust there. Now, this is probably not much deeper than surface level, so if you took a flap disc and cleaned all this off to bright and shiny, it won't rust any more than a base material. But in the state that this is in right now, this will get rusting and pitting. Again, probably not to the extent of steel, but you know, on something nice that you made out of stainless, you don't want to see rust spots. So it's in your best interest, if it's accessible and it's in an area that's visible, you probably want to clean this off and grind it down towards bright and shiny. Now keep in mind, this discoloration of oxidization is not a weak point in the case of most applications. It's just the corrosion resistance issues is going to be a problem for some. So now I'm going to wave cook a weld bead on this and make it real ugly just to show you what that looks like. So here's our little weld that looks a lot different than the previous ones. Now I did this with a number 8 cup, but yet this looks like it's kind of cooked. And no, it's not dull gray to the extent that you could definitely cook this to, but this doesn't look good. This dull red gray in the heat affected zone is a great sign that your gas coverage was poor. We have dull gray at the termination of the weld because as I was welding, I stopped and I pulled the gas coverage off while it was still hot. That's something you never want to do with stainless. At the end of a weld, make sure you keep that gas cup and the gas flowing to keep protecting that. But from a visual standpoint, this doesn't really look good. And I'm going to brush it now. We're going to look at it and we're going to make a determination if this has corrosion resistance. So this cleaned up a little bit better than I would have thought. However, it's still dull gray and it might be hard for you to see all around this weld area. And it's also dull gray in this section here. From a standpoint of corrosion resistance, this will likely get rust on it, a surface rust at least, on something that you actually made, especially in this area around here. Let's take a look at the back side of this and see what kind of garbage we have there. So now we're talking. Look at this junk here. If you see this where it's just completely dark gray, scaly, this is also known as sugaring. This is completely undesirable. Now, from a strength perspective, if I ground this down, the material there really isn't compromised structurally speaking. The issue here is, well, there is zero corrosion resistance. Imagine having this inside of a pipe weld with some kind of corrosive liquid. It's going to eat right through this. So that is an issue from that perspective. This can be a structural issue if the backside of a weld looks like this on something like a stainless car header. And the reason I say that is there's a lot of places that a crack could propagate from in here because of how janky and jagged edge this is. Not to mention, you can typically get some form of suckback or internal undercut on the sides of something like this. And on something like a header that experiences huge temperature swings and vibration, yes, it can very well crack over here or on the sides. Very, very common. And that's why back purging becomes really important. For a lot of things, like say some stainless furniture you're making, this is of little consequence. It's really not an issue. If you're making a race car header or a turbo manifold, you should really be back purging the inside of that tube with argon to prevent all of this from happening. And once again, like I said earlier, it's very common for guys just to run lower amperage to help prevent this from happening, and that can work, but you also run the risk of not fusing things properly, so it's kind of a give-take thing. And something critical, you need to run hot enough to melt things and get fusion and depth of penetration, and that generally means back purging. Now, the other thing I'm going to mention is what I said earlier, where you can use a backing bar to help cool it off. The other welds on this side that I did originally did partially look better because they were sitting on this table here, this tabletop, and that was pulling heat out of it. This was sitting out in open air, much like if you welded a race car header or something, and that is why the exposure to oxygen and how hot this got is just guaranteed to cause this. Now, let's try and brush this off and see what we can get. I don't have high hopes. And completely as I suspected, this is completely dark gray. We cannot clean this off. Even in this area, it's discolored compared to the base material. There's zero hope for this to regain the corrosion resistance. We'd have to grind through this quite a bit. And I'm gonna try and do that right now and see how far and how deep that goes in there. Hopefully you can see that about halfway through it's all bright and shiny again. So again, that was mainly surface level, a little bit under the surface. So if you were to grind this all the way down, you would likely regain your corrosion resistance. Again, the problem being that, well, you grind this all the way down clean, now you've kind of thinned out your base material, and on something as thin as this, it's probably just going to crack where it's thin due to how thin it became. So again, if the corrosion resistance or the overall performance is a must-have, you definitely want to back purge or at least put a chill block on it to help prevent some of the heat from oxidizing this. So now that you understand a little bit more about the oxidization of the material and the risks that come with that, I just want to talk a little bit about some tips for actually welding this stuff. Now in this video, I'm not going to have arc footage of the puddle. I'm in the part 2 of this video, I'm going to focus solely on techniques in welding stainless. It does weld similar to steel, but there's a lot to consider. But I want to give you some tips that'll help you out just learning to weld as a start. Number one is your heat input is absolutely critical. This is not a material that you want to take a long time to get moving and a long time to weld. It's kind of like a catch-22. You can use a big giant gas cup, but if you start welding it and you just move super slow, that heat affected zone is going to keep growing and you're going to get oxidization even with a really good cup. So you do not want to go super low amperage, super slow just to try and produce better welds. It can have an opposite backfiring effect with you. Likewise, you want to use enough amperage to where you achieve proper fusion. You don't want to run too cold and just put cold silver beads because they look good, because you're building junk basically. The welds will be likely to crack because they're so thin. When it comes to welding it, at the start of the weld, you want to boost the amperage a little bit to get that weld pool in existence, and then you want to move fairly quickly. Again, you don't want to sit there pumping heat in it at the start to get, say, a fillet weld to join together. You want to get that heat on there, get that weld pool established, and start moving. You're going to notice that the heat affected zone lines, that blue line on your weld, that's going to tell you a lot. If that line is jagged and it's not straight, that's telling you that you're inconsistent in your movement speed, and you don't want to do that with stainless. To get really clean, light straw to silver welds really requires absolute control over travel speed. The more consistent you are, the better your weld's going to look, the better the heat affected zone is, and that heat affected zone line will tell you what you're looking like. You can read so much from that because on stainless steel it turns pretty colors. On normal steel it's a lot harder to tell what's going on because it just doesn't react the same as stainless. It doesn't form that crystals on there that turn color. Another thing you want to be in a habit of with welding stainless steel is you want to, at the end of the termination of the weld over here, keep that gas coverage on for 6, 7, 8 seconds. Your post flow matters. If you just pull off of that at the end, that weld will oxidize because it's still hot, and then you're going to have color to it. Again, is that color a detriment? Typically not, but the difference between maybe a blue color and dull gray that's going to lose corrosion resistance is very close to one another, and it doesn't take much of you just hitting the end of the weld and popping off of it with complete disregard before it's going to start rusting there on something you built. And even with steel, be in the habit. You're motoring on, you're welding, at the end of it, keep that post flow there. If you have adjustable post flow, 6 to 7 seconds would be ideal. Once the post flow stops, then lift your tungsten off of the material and your weld should be okay. Once again, this is not harder to do than steel. It just requires more attention to detail. And that's one of the things where people, I think, get wrong mostly with welding, is most of the alloys like titanium and Inconel and all of those things in stainless, they're not really harder to weld than steel. They just require an attention to detail. So better surface prep than steel. You got to watch your heat input, your amperage and your travel speed must be spot on, and your gas coverage is far more critical. Like with titanium, it's very common to have your cup and then you have a trailing shield of 1 to 2 inches behind the cup that as you weld, that area behind the cup is still getting shielded, and that's how you produce, you know, very high quality titanium welds. It's not that the material itself is harder to weld than steel, it's that you require far more argon to get decent results, and stainless is the same way. You need to be up 30, 40 cubic feet an hour for a lot of stainless jobs to get acceptable results. And now that you know what to look for in your welds, you can make a better determination if what you're seeing in your welds are good or not, and you can make changes to make them better. So with that said, hopefully you learned something. If you get any comments or questions, feel free to leave them in the comments. And until next time.